Hi, and welcome to Chapter 36. Chapter 36 is on population ecology. I thought I'd start with an example of something really close to home as far as Montana goes. This is an elk being stalked by wolves, or hunted by wolves. Um, we've had huge elk populations in Yellowstone Park for a while, and we use hunting to kind of limit that. But in 1995, they reintroduced the wolves into Yellowstone Park, and you can see that their population has taken off since then. If I remember right, I think we have around 1,000 wolves in Montana right now in 2009. And so it's really taken off. What kind of a growth pattern do we see? We see what's called exponential growth pattern. Will it do that forever? No. And so the population is starting to taper off as well. And so this chapter is about populations, how they change, what are characteristics of populations. First thing that's important is what's called the N value. Capital N value stands for the number. In other words, how many individuals are there? Are there 1,000 wolves? That'd be the N value. Next thing is how dense they are. Obviously, to have 1,000 of anything isn't a big deal, but if they're all congregated in one area, then that's going to be a high density. So obviously, Montana is going to have low density compared to like India, for example, the parts of India. Dispersion is another example of that. In other words, these are fish that are swimming in a school, and so we call that clump dispersion. We can also have uniform dispersion. If you look at this, if you were to squint at a bird population from high above, it just looks really regular. Why is that? Well, they're defending a little territory. This is their little place where they get to defend their little egg, and so we get this uniform distribution. Sometimes it's random, but it's probably not random. In other words, there's probably more chemicals, more water in areas where there are a lot of dandelions, and so it's going to vary a little bit. So we've got how many there are, how densely it's packed, and then where it's dispersed. Another example of a population is what happens during its lifetime. We call that its survivorship curve. If you look at life, there are actually type 1, type 2, and type 3 survivorship curves. Type 3, if we think about an oyster, for example, oysters create literally millions and millions of offspring, and this is a percent of how many survive. And if you look on right here, it's just like awful from the beginning. In other words, they almost all die, but a few of them survive, and those that survive live a long period of time. And so that's one strategy of survivorship. Another one could be the life strategy type 2 of the squirrel. If we look at this, it's linear relationship. What does that mean? Squirrels are dying randomly that whole time. It's not like they all die right away, but during the course of their lifetime, they're going to be dying at a linear fashion. And then if you look at us, people who dress like this are humans, we're all going to survive childhood. In other words, we have parents that take care of us. There's a high amount of care. And so we almost all survive, and then we all die right at the end. In other words, when we get to be 70 or 80. Each of these has its own advantage. And so if we look at populations and how they change, there are two trends. The first one of those is going to be called exponential growth. Exponential growth is going to be growth whenever we have a positive growth rate. And I kind of skipped that. Here's two more letters that you got to know. So N is how many there are. R is the growth rate. In other words, is it positive or is it negative? And then the last thing is K, and K is going to stand for carrying capacity. That's the average organisms that a area can support. You can think of it that way. And we'll get to that on the next slide. R then is going to tell us, is the birth rate higher than the death rate? If the birth rate's ever higher than the death rate, then we're going to show exponential growth. Darwin did this little calculation on elephants and found that within something like 750 years, even though they have this really long gestation period, you'd have literally billions of elephants. And so all species will undergo exponential growth, and we'll look at human population in just a second. But eventually, something happens. And so these, again, are just mathematical relationships. There's nothing in here that's actually data that's been collected. So this would be the exponential growth trend, but here's that K I was pointing to a second ago. In other words, there are two trends. This would be the trend of exponential growth, but it doesn't go on forever because you run out of certain supplies. And so eventually we have what's called logistic growth, where you eventually hit what's called a carrying capacity. And so we sometimes call that a sigmoidal growth pattern. In other words, it averages out. The reason that happened is that we have limiting factors. In other words, we run out of food, we run out of space, we run out of shelter. And so this is a snowshoe hare. Snowshoe hares are fed on by Canada lynx. And what we find is their populations will increase, then they run out of food, and then they'll decrease. And then there's enough food, and they'll increase, and then they run out of food, and they decrease. And a cool thing in this picture is that the lynx populations, you can see that they're shifted a little bit to the right. And that's because they're feeding on snowshoe hares. And so they're kind of tied to this boom and bust life. These two terms then, R selected and K selected, do you remember what R stands for? That's growth rate. And so there are kind of two different evolutionary strategies. There's the strategy of those who grow really, really quickly, and so you can think of that like a bacterial infection, or this could be the growth rate in aphids, but then eventually they crash again. And so that works if you have a really short reproductive cycle. If you don't live that long, it's better to be R selected. But for a lot of mammals like us, that would be too hard, and so we are what are called K selected. In other words, we've evolved to create this nice logistic growth pattern where we increase and then we eventually level off. Now, wolves in Yellowstone Park, we're starting to see that as well. When there's plenty of food and there weren't a lot of wolves around, they were having huge litters, and sometimes actually 2 litters for a group of wolves, which is pretty unheard of. But now that there are a lot of wolves, we're starting to see that they are reducing litter size, and so they're starting to find that, hopefully my hand is in the video, they're starting to find that logistic growth pattern. Now, what are humans doing? If you look here, man, that looks like exponential growth. And it is exponential growth and has been exponential growth. Here we are today. But what's eventually going to happen, you can see this is population increases. Is it projecting over the next 50 years we're going to see a decrease in that? And so you can see that eventually we're going to level off and have logistic growth as well. And so not all is bad for us. How can they figure that out? Well, one good way to do that is to think about 2 things. First of those is called demographic transition, and then the other one is called the age structure diagram. And so this is the United States. What we're looking at here is birth rate in blue and death rate in red. And what we found is that around the turn of the century, we've seen a really sharp decrease in the death rate. And that's with modern medicine. You're always going to decrease the number of people who die. But it takes a little while for people to realize that and start having fewer kids. And so now we're seeing later on we've got this decrease in the rate of births. If I remember right, this is actually from Mexico now that I think about it. And so it takes a while for after that death rate to decrease to have a birth rate that decreases as well. But once these two hit, then we get a leveled population, and eventually we have logistic growth. Now you can also look at age structure diagrams. And so age structure diagrams, look at this first one. This is in 1980. And we can see how many people are male and how many people are female in each of the different age groups. So this would be example would be 0 to 4, or we could find like my group. I was born in 1969, so this would be me, and it shows me what percentage of the people were in my age group. But you can see right ahead of me are going to be the baby boomers, so we have a huge increase in this population. So by the year 2005, that baby booming group is going to move up to here, and then by 2030, they're going to disappear. And so if you ever get an age structure diagram that's really fat on the bottom, and this was fat on the bottom for a while, when these were all shifted down, that's going to be a population that's going to show exponential growth. And so we can go to some places like Kenya, for example, and you have so many people who are in those younger groups, and that means that over time they're going to increase. So it looks kind of like this. Now the troubling thing is once you decide, oh, we've gone through the demographic transition, let's stop having so many kids, it takes a while because this group gets shoved to this group, they have more kids, and so we think of that as having population momentum. In other words, once it gets started, it's kind of hard for that to stop, but eventually will, and so not as all bad for humans. A more important thing to think about, though, is our ecological footprint. In other words, it's not fair where we are on how much we're actually consuming. And so this is an average family in India. I think this was a study done, it's just a photo study done in Life magazine. So they have all their possessions laid out in front of their house. And you can imagine on the next slide is going to be an American house. And these are all the possessions that we have. And so what does this mean? Well, our population is lower than that of India, but we have a much higher ecological footprint. And so if you play this out, in other words, how much I'm consuming per person, so I'm using 5.4 hectares per person to make all of the stuff I need, and we compare that to some place like Africa, you can see that we're using a disproportionately higher amount of our goods. And hopefully that's another thing that we eventually start to see leveling out.